Okay, welcome everyone. We will come back to this as usual a little bit later in class. Let's get started with some announcements. So first of all, problem set 2 is now available. It will be due on October 9th at 11:59 p.m. Montreal time. You can find the problem set both on the Slack workspace and also in my courses, if you have access to my courses. There are instructions also for submitting it. Please remember that this problem set should be submitted in LaTeX. Again, there is a template for how you can write up your LaTeX solutions, and that should be available with the problem set. And again, also, the LaTeX will not be graded in the sense that if you make a small LaTeX mistake, that's not a problem. The goal is to get you to become more familiar with LaTeX, and also it just is easier for us to read. But yeah, so please do use LaTeX for your solutions. And there are resources on how to learn LaTeX in the first lecture. And then there are office hours today right after class, so please stick around. Office hours will just be in the same Zoom room that we're currently in, so yeah. Are there any questions about the course? Okay, well, let's get started. So there is a lot of stuff that we're going to be covering today regarding linear algebra. This is the second of 2 classes on linear algebra. We're going to really dive into a lot of different things today. So please let me know if there's something that isn't clear, and I will make sure to go into more detail on that. Let's start out with linearly independent vectors. So this will be really important in a bunch of contexts. A set of vectors is said to be linearly dependent if there are coefficients with at least one of them being non-zero, such that you can combine the vectors to get 0. Now, the reason why there's that condition at least one of them is non-zero is if you just made all of them 0, then this would be sort of trivial. So you have a linear dependence if you can combine them in some non-trivial way to get 0. If there isn't such a thing, then we say the vectors are linearly independent. And linearly independent vectors are super important. There's a geometric interpretation of this, which is if you have some k linearly independent vectors, then they're going to define a k-dimensional linear subspace. I realize this is really hard to visualize in higher dimensions. So let's think about it first in 3 dimensions. In 3 dimensions, if you have one vector, it is linearly independent with itself, sort of, yeah. So that one vector and all scalings of it are a line through the origin. If you have 2 vectors, if they are 2 vectors being linearly dependent means that one is just a multiple of the other. And so if you have 2 linearly dependent vectors, then they define a line. But if you have 2 independent vectors, then they define a plane through 3-dimensional space. And in higher dimensions, you could also have 3 linearly independent vectors, which would define a 3-dimensional subspace, or 4, which would define a 4-dimensional subspace, and so on. As an example, these 2 vectors in 3-dimensional space are linearly independent. So the vectors formed by all of their linear combinations form a 2-dimensional plane. And as an example of something else that's in that plane, 10, 1, 1 is in this plane. Well, why is it in that plane? Because you can combine these 2 vectors to create 10, 1, 1. You just take C1 equal to 10 and C2 equal to 1/2. So that means that we have this vector is a linear combination of the others. And since 10, 1, 1 is a linear combination of these other vectors, that means that all 3 of them are linearly dependent. But yeah, so 10, 1, 1 is in this plane, and all of those things together form a 2-dimensional subspace. There's a question. For the linear dependence definition, is the 0 on the right-hand side of the formula a scalar 0? No, good question. I'm sorry, I should have maybe indicated. I'm using 0 here to mean a vector 0, so a vector that is all zeros. And I think that I'll generally use that. That's often done. Sort of 0, if the dimensions work out so that it's a vector, then it's a vector. If the dimensions work out so it's a scalar, then it's a scalar. Sorry, I didn't say that. Good catch. How many linearly independent vectors can there be in R to the n? Yep, you can have n. Because each one is going to increase, each new one increases the dimension of your linear subspace. So if you had 5 linearly independent vectors, then you have a 5-dimensional subspace, and you can never have a larger dimensional subspace than the ambient space. So you could never have like an n+1 dimensional hyperplane in n-dimensional space. You'd have to go to n+1 dimensional space. Okay, so that's basics of linearly independent vectors. Now, we'll use these immediately in order to think about matrices. So the column rank of an m by n matrix is the number of linearly independent columns of the matrix. Likewise, the row rank is the number of linearly independent rows. I guess I should say the maximum number. So as an example here, what are the row and column ranks of this matrix? So the column rank is going to be, let's think about it. The column rank we have, this is just 0, so we don't have to think about that. This is the same as this, so they're definitely linearly dependent. And these 3 are all linearly independent. So we have 3. The row rank. Now, this first row can be written as a combination of the second and third rows. You just take 2 times the second row plus 1 times the third row, and you get the first row. So we have only 2 from the first 3, but then the fourth is also linearly independent. So we have 3 linearly independent rows. So the row rank and the column rank are both going to be equal to 3. Are the row and column ranks always equal? If so, why? What are people's thoughts? Are they always equal? Yeah, the row rank of a matrix is equal to the column rank of its transpose. But is the row rank of a single matrix equal to the column rank of itself? Okay, there's some disagreement. So, suppose that a matrix has column rank R. Then there have to be some R vectors such that every column of A is a linear combination of them. That's what it means to have column rank R. Let's write this down. These are the column vectors. And we're writing A as each column of A is going to be some linear combination of these column vectors. So we can just write that as A as a product of the matrix with these column vectors and these weights. So this first column is just a linear combination of the column vectors, and that gives us the first column of A. These weights, if we dot that with this, we get another linear combination of the columns. And so this is just capturing the matrix A is a linear combination of these columns. That's all it's saying. Okay. Let's just express this as A equals V times W. Now let's take the transpose. If we take the transpose, A transpose is equal to W transpose times V transpose. Great. Which means that the columns of A transpose are, just by the same logic, linear combinations of the columns of W transpose, this other matrix, this matrix of weights. Okay. So what does that mean? Well, the columns of A transpose are the rows of A. So if we know that all the columns of A transpose can be represented as linear combinations of the columns of W transpose, then the row rank of A is at most the number of columns of W transpose. It's at most the number of columns because since all of the columns of A transpose can be written in terms of the columns of W transpose, all of the rows of A can be written in terms of the columns of W transpose. And so there might actually be more columns than we need. So the row rank is at most the number of columns. And the number of columns is just the number of rows of W itself, which is R. Okay, so now what do? We've just related we assume the column rank is R. You know, the row rank is at most R now. Why couldn't it just be the row rank is less than or equal to the column rank? Ah, yes. So we can also just do the same. So this is what we got from what we did just now. Sorry, row rank is less than or equal to column rank. We could also do the same thing with A transpose and show that the column rank, sorry, show that the row rank of A transpose is less than or equal to the column rank of A transpose. But that just means that the column rank of A is less than or equal to the row rank of A. I realize there are a lot of transposes going on. I would encourage you to just take a look at the slide afterwards. It's not actually difficult. It's just there are a lot of transposes floating around. But yeah, so doing the same thing with A transpose, we can show column rank is less than or equal to row rank. And since each of them is less than or equal to the other one, they have to be equal. So yes, they are equal. Questions? Okay. So that means we can just refer to the rank of a matrix. We don't even have to say row rank or column rank. For matrices A and B, what can we say about rank AB in terms of rank A and rank B? There was a question about m equals n. Everything we did before was actually the case regardless of the dimensions of the matrix. It didn't have to be a square matrix. So is it true that the ranks multiply? If you have the rank of A and the rank of B, is the rank of AB equal to the product of the two? Or the sum of the two? It couldn't be, because if rank A and rank B were, like, suppose they were what's called full rank. Suppose they were n by n matrices and they each had rank n. The rank of AB can be at most rank n, because you can never have more than rank n in n-dimensional space. So you can't have it be the sum, you can't have it be the product. So the columns of AB are linear combinations of the columns of A. So the rank of AB is less than or equal to the rank of A. The rows of AB are linear combinations of the rows of A. So the rank of AB is less than or equal to the rank of B, too. So That is some stuff that you can say. It's not necessarily true that you can add the ranks. In fact, in general, that will not be true. If A and B have rank n, then rank AB can be at most n. What is the rank of the n by n identity matrix? Yep, that is just n. All the columns are linearly independent, so the rank is n. That's called full rank. It's as high as you can get for an n by n matrix. In general, how high can you get for an m by n matrix? What is the maximum possible rank for an m by n matrix? Yeah, whichever is lower. Because if m is less than n, then you have m rows. And you know that the rank is equal to the row rank. And clearly, you can't have more linearly independent rows than you have rows. So it's going to be the min of m and n. Or sorry, it's at most the min of m and n. That's the maximum that it could possibly be. It could be less than both m and n. Okay. Let's look at inverse matrices. So if A is a square matrix, then an inverse matrix to A, if it exists, is a matrix B such that A times B is equal to the identity matrix. Let's take a look at some facts for inverse matrices and prove them. First, if A has an inverse, then the rank of A is equal to n. Why is this true? So if AB is equal to I, then we know that the rank of A is greater than or equal to the rank of I because of that product thing that we saw before. But the rank of I is equal to n. And since it can't have rank more than n, then A has to have rank n. Okay. Now what about the other way around? If rank A equals n, then A must have an inverse. This is the converse. So we know that at most n linearly independent vectors are possible in R to the n. So that means that every other vector in R to the n can be expressed as a linear combination of the columns in A. But that means that there is some B that gives us AB equals the identity. The reason being that the columns of B are just exactly those linear combinations. So the first column of B is like whatever linear combination of the columns of A you need to get the first column of I. The second column of B is whatever the coefficients are for the linear combination of the columns of A that gives you the second column of I. And since each of the columns of I, there is some linear combination of the columns of A, we can have this matrix B. This doesn't, say how to construct it. It just says that it exists. Okay, so now because of these two facts, we know that if A is an inverse, then the rank of A is equal to n, and vice versa. If rank of A is equal to n, then A must have an inverse. Okay, next fact. Though I wrote that as face. Did I write them all as face? No, I only wrote those. I only made this misspelling. So this is face number 3. Inverses are unique. That is, are there two different inverses that are possible? So suppose that there were two different inverses. A times B1 is equal to the identity, and A times B2 is also equal to the identity. Suppose that were true. Could that be possible? Well, in that case, we could just subtract these two, and we'd have A by distributivity, which we didn't actually prove. We didn't prove that matrices do this, but it's fairly easy to show that matrix multiplication is distributive. So AB1 minus AB2 is equal to A times B1 minus B2. But since those are the same thing, then that has to be equal to 0. However, that means that there is, if B1 and B2 are not the same, that means there's some non-zero combination of the columns of A, which is equal to 0. This is the zero matrix here. But there can't be some non-zero combination of the columns equal to 0. That would mean that the columns would be linearly dependent. But they're not linearly dependent because the rank of A is n, since matrices only have inverses if the rank is equal to n. So there can be only one inverse. If there's an inverse, then it's unique. And finally, the final face. If you have a right inverse, then that is also a left inverse, i.e. if A times B is equal to the identity, then B times A is also equal to the identity. So let's prove this. Now we know that if AB equals the identity, A is invertible, so the rank is equal to n. And that means the rank of its transpose is also equal to n because column rank and row rank are just the same thing. That means that A transpose has an inverse. Let's call that inverse C transpose. Now, because C transpose is an inverse of A, we have A transpose times C transpose equals I, just by the definition of C transpose being an inverse. But we can take the transpose of that. And since I is its own transpose, and since multiplication flips when we take the transpose, we get C times A equals I. Okay, so now we have that there is a left inverse of A. Why is this left inverse equal to B? Well, we can just use associativity, which we proved last time. CAB is equal to C times AB, but since AB is equal to I, it's equal to C. But CA is also equal to I, so CAB has to be equal to B. That means that C is equal to B. So the left inverse and the right inverse are the same, and they're both unique. So if a matrix has an inverse, you can multiply it on either side and you get the identity. Any questions? Yes, the inverses are also going to be full rank. Because, I guess I didn't say this, but the inverse of an inverse is the original matrix. And it's sort of easy to see that from this. So since A has an inverse, A inverse also has an inverse, which means that it has to be full rank as well. Okay, this is how we'll typically write A inverse, A to the negative 1. Cool. Okay, now we've seen a lot of things. Let's see how we can use this. So one simple way where inverses turn up, inverse matrices will turn up all over the place, but one simple way is in solving systems of linear equations. So for example, this is a system of linear equations. That means there are no squares or anything going on. The variables they're multiplied by constants, added together, and there's some constant. So this system of linear equations can be represented in matrix form as A times V equals B, where A is your coefficient matrix, V equals the vector x, y, z of your variables, and B is just the constants. You can see that A times V is exactly the left-hand sides of all of these equations, and B is just the right-hand side. So as a vector equation, A times V equals B, is just the same as this entire system of linear equations. So if this system of linear equations has a solution, then it is that corresponds to any solution to this vector equation. Now, why is this better, representing it as matrices? Well, because there are ways to get the inverse of a matrix. I'm not going to go into inverse algorithms, but you can get the inverse of a matrix. And if A is invertible, then the unique solution here is given by V equals A inverse B. So you can just do this with matrix multiplication. Now, why is it unique? Why is it the unique solution? Well, you just multiply on both sides by A inverse, if A inverse exists, and you have V equals A inverse B. That's just what you get. So this is actually a proof that if A is invertible, then there is exactly one solution to this system of linear equations. Okay. Orthogonal matrices. An orthogonal matrix is one where A transpose A equals the identity. So A transpose is just the same as A inverse. Here are some examples of orthogonal matrices. For example, the identity itself is an orthogonal matrix because its inverse is just itself, which is also its transpose. Permutation matrices are also orthogonal matrices. You can imagine taking the transpose of this. I realize it's a little bit hard to see. Or you can imagine, you can imagine multiplying this with its own transpose. And you can get the identity out. And then this is what's called a rotation matrix, which we'll see in a bit. What does it mean to be an orthogonal matrix? Well, if something multiplied by its transpose is equal to the identity, then you imagine, what is something multiplied by its transpose? Well, it's this, to get this multiplied by its transpose, you take the first column and you dot it with the first row of the transpose, which is the first column. So this column dotted with itself is the first thing in the product. This column dotted with these other columns gives you the first column of the product. So if A transpose A equals the identity, then this column dotted with itself has to be equal to 1, the first entry in the identity. This column dotted with this column has to be equal to 0. This column dotted with this column has to be equal to 0. Then if you look at the second column, you have this column dotted with this column has to be equal to 0. This column dotted with itself has to be equal to 1. This column dotted with this other column has to be equal to 0, and so on. And in general, an orthogonal matrix is saying that every two different columns have dot product 0. And if you dot the product, a column with itself, it's 1. That's just equivalent to being an orthogonal matrix. And if you didn't get it from this picture, just write out a matrix and see what it means to multiply A transpose A. So condition number 1, every two different columns have dot product 0, means that any two columns are perpendicular vectors. And the reason for the term orthogonal is that that's also called orthogonal. Any vectors are orthogonal if they are perpendicular. It's the same thing. The second thing means that the norm of every column, the L2 norm of every column, is 0. Okay, there are a couple of questions. Are the columns linearly independent? Yes, they are linearly independent because any two pair, they are going to be linearly independent. The reason why is actually they're linearly independent because this matrix is invertible. So it means that it has full rank. So the columns are always going to be linearly independent if the matrix is invertible. Are orthogonal and orthonormal synonyms? No, though in this case they are orthonormal. Orthonormal means both of these properties hold, that the norms of everything are 1, and that they are also orthogonal. So here it's orthonormal, but in general, orthonormal vectors also have to be unit vectors. Don't worry if you didn't get that. Okay, so these conditions mean that the columns of an orthogonal matrix form what's called a basis. And you should think of a basis being basically a different set of coordinate axes. So instead of using the x, y, and z axes, what you've done is you've changed your axes. And instead you have these 3 other vectors, if you're in 3-dimensional space, where x, y, and z are still unit length. So instead of 1, 0, 0, 0, 1, 0, and 0, 0, 1, you now have 3 other vectors that are still length 1, and they're still mutually perpendicular, but they don't necessarily point along x, y, and z. So the easiest way to think of this is doing some sort of rotation. That's actually not the only thing you can do. You could also do a reflection and, yeah, other stuff. But the easiest way to think of it is sort of rotating the space. So here's an example in 2 dimensions. In 2 dimensions, orthogonal matrices include rotation matrices. Rotation matrices look like this. Now, why is this an orthogonal matrix? Well, we take this column, we dot it with itself, we get cosine squared plus sine squared. Cosine squared plus sine squared is always equal to 1. We take this column, dot it with itself, we get the same thing. If we dot the 2 columns together, then we get 0 because these cancel out. So it's orthogonal. And what is the geometric interpretation? Well, the geometric interpretation is that we've actually rotated x and y by angle theta to get these other 2 columns. And the columns are cosine sine and negative sine cosine. And this is cosine sine, this vector, and this is negative sine cosine. So those are the 2 new basis vectors. I'm not really going to go into what basis means, but this is sort of an intuition for why bases are important. For example, you can use this rotation matrix to do rotations. If you want to rotate the point 3, 4 by 45 degrees, you can just take the rotation matrix for 45 degrees, multiply it by 3, 4, and if you work out what that is, you get this other point. 2 questions. First of all, is this what is called a linear transformation? All matrices are linear transformations. Second question, does this mean that all orthogonal matrices in 2D are rotation matrices? No, but in 2D, there are rotation matrices, and then you can also reflect something. So reflecting just corresponds to swapping the order of these 2 columns, so that instead of having x, y look like this, you sort of reflect across something, and that just changes the signs of various things. So all orthogonal matrices are rotation matrices or the reflections of rotation matrices. Okay. Let's get started with determinants, which will be super important. Now, there are a lot of different definitions for a determinant. I'm only going to go through a couple, and I'm not really going to show why they're all equivalent, partly because it's just messy, but I encourage you, if you want, to delve a little bit more deeply. So the determinant of a square matrix can be defined recursively. If it's a 1-by-1 matrix, then the determinant is just equal to the thing, that one entry. If it's a 2-by-2 matrix, then you take the product of the 2 diagonal entries and you subtract the product of the 2 off-diagonal entries. If it's a 3-by-3 matrix, now it gets a little bit more thorny. You can do it recursively here. You take this first entry, A11, and you multiply it by the entire determinant of this submatrix, this 2-by-2 submatrix, caused by the second and third row and column. Now, why the second and third row? It's because you cut out the first column and the first row, which are where this entry A11 is. Now, then that's not all of the determinant. You also subtract A12 times the determinant of what happens if you kill this row, the first row in the second column. And then you add A13 times the determinant of what happens if you kill the column and row of A13. And in general, this will be alternating the sign. So how does this work in general? For an n by n matrix, you can define it recursively or inductively, if you like, by letting A sub k be the matrix where you delete row 1 and column k. Then determinant of A is going to be A11 times determinant of A1, if you killed row 1 and column 1, minus A12 times the determinant of A2, plus, minus, and so on, until you get to plus or minus times A1n times the determinant of an, which is what happened if you killed row 1 and column n. Are there questions about this definition? Okay. So again, this is the definition, recursive formulation of the determinant. If you expand this out, what it's going to look like is going to be the sum or difference, or it's like sum and differences, they're going to be plus and minuses, of a bunch of different products. And the products are going to look like this. Now, what are these products? Where did these products come from? Well, actually, these products are all the possible products that have one entry in each column and also one entry in each row. So for example, A13, A21, and A32. These three things, if you plotted them, this would be a permutation matrix. These three things, because there's one in every row and there's one in every column. And all of these 6 different terms are the 6, which is 3 factorial possible permutations of 3. In general, there will be n factorial different terms in the determinant. Now, how do you determine what the signs are? These are plus and minus. The sign of the product is going to be the sign of the corresponding permutation. And I didn't tell you what the sign of a permutation is. You can look it up if you're curious. That goes into group theory. But it's really cool, and it turns up in a bunch of math. There's a question, sum of diagonals minus sum of the negative diagonal. So you're always going to have the sum along this diagonal, and that's always going to be positive. That's just the permutation, which is the identity permutation. And then you are going to have this sort of anti-diagonal. And I guess the sign of that is going to depend on the sign of the overall, or the parity of the overall matrix, right? Did I mess up the signs here? I don't think I messed up the signs here. Yeah, sorry if I messed up. Sorry if I messed up any of the signs. Yeah. Cool. Okay. So are there any questions about this? Awesome. So here are some determinant facts, which we're not going to have time to prove, unfortunately, or not all of them. First, which is really cool, the determinant actually has a geometric interpretation. It is the volume of this thing formed by the columns of the matrix. So if the columns of the matrix are like this, then you can write these vectors in 3-dimensional space, if it's 3 dimensions, and create this. It's called a parallelepiped. It's the higher dimensional analog of a parallelogram, and you can do it in any dimensional space. And this thing is basically just a skew box. It's like a box that's been scrunched a little bit. It is also equal to the area in 2-dimensional space. But in n-dimensional space, it will be equal to the n-dimensional volume of this parallelepiped. So area in 2 dimensions, volume in 3 dimensions, higher dimensional volume in higher dimensions. And it's plus or minus because there's a sign involved. And the sign there's this thing called weighted volume or signed volume. We don't have to get into that. Depends on basically the order of the columns in the matrix. Okay, this is really cool. And from this, we get actually a really cool, basically the most important fact about the determinant. So determinant is 0 unless the columns of A span the whole space Rn. So if they span the whole space, that means that they are linearly independent. So you actually have a box with non-zero volume. So for example, in 3 dimensions, if they're linearly independent, then you get a box with 3-dimensional volume. But if they aren't, then you get a box, but you're trying to calculate the 3-dimensional volume of a 2-dimensional box. If you calculate the 3-dimensional volume of a 2-dimensional box, you have 0 3-dimensional volume. So if you don't have the column spanning the whole space, then the volume is 0. And so the determinant is 0. That means that all of the following are equivalent. If the determinant being non-zero, A having full rank, the columns being linearly independent, and A being invertible. We already knew these last two were equivalent. But all 3 of these are equivalent. Determinants non-zero, full rank, invertible matrix. Okay. Something else, which is sort of easy to see. The determinant of the transpose is just the same thing as the determinant. Nothing that we did mattered if you took transposes. Here's something that's not as easy to see. The determinant of the product is equal to the product of the determinants. So ranks didn't multiply, but determinants do. Are there any questions? Okay. Now let's go to eigenvalues and eigenvectors. We can discuss the product formula later. I'm sorry that that I don't have time to prove things. Eigenvalues and eigenvectors. So an eigenvector of a matrix is any non-zero vector such that a non-zero vector x such that ax is equal to some constant times x. The value lambda is called an eigenvalue. This is a scalar value. So they come in sort of eigenvector, eigenvalue pairs. And there's a geometrical interpretation of this, or in general, you can think of an eigenvector and an eigenvalue for really any transformation on vectors. Any transformation on vectors has eigenvectors, which are just like the vectors that don't like move, they just get bigger or smaller. So for example, a rotation, yeah, I won't go into that, but yeah. The value lambda is called an eigenvalue. Okay, so let's take a look at an example. Here is a matrix. If I multiply it by 2, 1, then I get 6, 3, which is just 3 times 2, 1. So 2, 1 is an eigenvector of this matrix, and it has eigenvalue 3. Okay. Now, notice that if x is an eigenvector with eigenvalue lambda, then any multiple of x is also an eigenvector with the same eigenvalue. That's because if you just multiply it by a constant, then both sides of this will multiply by a constant. Okay. Also notice that the eigenvalue could be 0. In practice, since we can scale the eigenvector, we often scale it so that its norm, its 2 norm, is equal to 1. It's a unit eigenvector. But eigenvectors don't have to be unit length. You can scale it to any amount. Okay. So let's look at the characteristic polynomial, which is going to tie a lot of these things together. We can write ax equals lambda x as A minus lambda identity x. And that is something we want to be equal to 0. Right? Here we're looking at the n-dimensional identity matrix. Now, when does this have solutions apart from x equals 0? So if A minus lambda I is invertible, then we could just multiply both sides by its inverse. Great. And we have a unique value, which is x equals this thing inverse times 0. Oh, shoot, x equals 0. So x isn't an eigenvector. No eigenvector can be the 0 vector. So if we hope to have an eigenvector here, we can't actually have A minus lambda I be invertible. It has to be non-invertible. Now, let's think back in our mind. When is something non-invertible? Well, it's non-invertible when there's a linear dependence between the rows, or between the columns, and it's also non-invertible if the determinant equals 0. So we can just see what happens, when we will get the determinant equal to 0. Notice that the determinant is a degree n polynomial. And that's because we had all these products of n different entries in the matrix. For example, if the matrix A is equal to this, then A minus lambda I is equal to this matrix, and the determinant is actually this quadratic polynomial in lambda. So when is that equal to 0? Well, it's just 0 at whatever those roots of the polynomial are. And in this case, the polynomial is going to have roots of 3 and 1. This is called the characteristic polynomial. And the characteristic polynomial's roots are just the eigenvalues, which means that there are n eigenvalues for an n by n matrix. There might be some repeats. And the eigenvalues might also be complex numbers. I realize we didn't really talk about complex vectors. Eigenvectors could end up being complex. All of the things we talked about also work for complex vectors. Whew. So, remember that problem at the start of class? The trace. The trace of a square matrix is the sum of the diagonal entries. Now, why is it even really important to look at the sum of the diagonal entries? It feels a little bit weird that diagonal entries matter more than other entries. Well, first, here's an example. This is a matrix with trace 4 because it's 2 plus 2, 4. As we saw, if you came a little bit early to class, the trace is the sum of the eigenvalues. Why is that true? Think back to our characteristic polynomial, which is the determinant of A minus lambda I. Let's look at the lambda to the n minus 1 term. This is a degree n polynomial. You can look at the lambda to the n minus 1 term. The only way to get products lambda to the n minus 1, remember all the lambdas are along the diagonal. The only way we can get the only way to get a lambda to the n is by multiplying all the diagonal entries. That would give us actually lambda to the n times -1 to the n, because all of these lambdas are negative. Now, what happens if we get, how do we get the lambda to the n minus 1? Well, we multiply all of the diagonal entries, but for one of them, we don't consider the lambda, we consider the 2. So I realize it's hard with a 2 by 2 matrix, but here it's the lambda to the n minus 1 is caused by a lambda and a 2, or this lambda and a 2. And if you had 3 of them, it would be 2 lambdas and a 2. 2 lambdas and whatever is over here. 2 lambdas and this other 2. And what this is basically Vieta's formula. The coefficient on lambda to the n minus 1 comes just from the product of the diagonal entries. That's the only way that you can get a lambda to the n minus 1. All of the other products in the determinant, remember the determinant is a sum and difference of products, none of the other the products will contain a lambda to the n minus 1. They'll contain lambda to the n minus 2 at most, actually. And the coefficient of lambda to the n minus 1 in this is just the sum of all of these things. And that's the sum of the diagonal entries, which is the trace. So in this particular case, the sum of the diagonal entries is the trace 4. Here we have lambda squared minus 4. So the trace is 4. The sum of the roots is 4. And the sum of the roots are, in fact, 3 and 1. The eigenvalues are 3 and 1. Whew. Now, why is the determinant the product of the eigenvalues? Yeah, the determinant of the matrix. Remembering back to Vieta's formulas, where the product of the roots is going to be plus or minus the constant term. Or it's going to be the constant term divided, plus or minus the constant term divided by the first term. And let's look at the constant term of the characteristic polynomial. We can get the constant term just by setting lambda equal to 0. So the constant term is just determinant of A. So by the Vieta's formulas, the product of the roots equals determinant of A. And in this case, the roots are 3 and 1. The product is 3. The determinant is 2 times 2 minus 2 times 1/2. That's the formula for a 2 by 2 determinant, which is 3. I'm going to skip over this because we're at time. But next time, we will wrap all of this up and we will tackle graph theory, including graph theory that uses matrix algebra. Feel free to stick around if you want to hang out at office hours, ask questions about the p-set or anything else. And thank you for sticking through all of that very, very fast introduction to the math behind determinants and eigenvalues and matrix inverses. I am happy to stick around also for questions about the